And I've seen this is the only thing which you will do today. So traffic flow theory is a set of mathematical models, mathematical equations which relate basically speed, flow, and density parameters. When traffic flow theory was developed, it was mainly related to macroscopic parameters. So we will look at in traffic flow theory, we will look at equations and the method to relate traffic flow macroscopic parameters. Okay, speed, flow, and density. So this theory or the concept of this theory was given by Bruce Greenshield in 1930s. So he was a US traffic scientist, you can call him. And in 1930s, he said that, okay, these three parameters, speed, flow, and density are related to each other. Okay. And the first relationship which he gave was between speed and density. The first relationship he gave in this context was between speed and density. So he said speed and density are related to each other with a linear descending straight line. Linear descending straight line, which you can see here in this figure as well. So according to Bruce Greenshield, speed and density are related to each other with a straight line, and the relationship between them is linear descending. Okay. Now we will try to develop other equations using the Bruce Greenshield model. Okay. Let me see if I can. Yes, I can. Okay. Starting to like it. So somebody suggested that I should be using, notebook. So you have the calculations saved with you. So what I've done is I have created two sections in the notebook, and with each class, I will add a page in the notebook. So each class calculation will be in a new page. Okay. Okay. Can I move it? Yeah, I can. Okay, so what is the equation of a straight line? According to Bruce Greenshield, speed and density are linked with a straight line. So what is the equation of a straight line? Yeah, anyone? Should be easy. What is the equation of a straight line? Everybody should know about it.
Y equal mx plus c.
Y equals mx plus c. Okay. Now tell me what is. So for this graph, make it bigger. In this graph, y is speed and x is density, right? So I will say speed equals to m into density plus c. Now when you said y equals mx plus c, what do you mean? What is c?
Constant.
Which constant? Which value from the graph?
Y-intercept.
Y-intercept. Okay, so how much is the y-intercept here? 65. Now remember, I'm just showing you with an example how to develop the relationship between speed, flow, and density. So these numbers are part of the example. The important thing is the procedure. So we will cover two examples so that you know the numbers can change. The numbers can change. So somebody plotted this graph between speed and density, and according to this graph, the y-intercept is 65. Y-intercept is 65. What is y-intercept? This is the maximum speed, right? y-intercept is the maximum speed. Let me see if I can. Okay, so according to this graph, y-intercept is 65. Okay, so I can replace c with 65. Okay, and what was m?
The slope.
The slope.
M is the slope. M is the slope. Okay, so slope means slope is y upon x, right? Slope is y upon x. So for the case of this figure, y is 65, and let us see how much is x. X is 110. See here, this is 110. Okay, so m is 65 upon 110. Now what is this? 65 is the maximum speed when density is 0. 65 is the maximum speed when density is 0. Okay, and what is maximum density here? So what is 110 here? 110 is the maximum density when speed is 0. Okay, so now my question is what I explained last time as well. What do we call the maximum speed when density is 0? Speed is maximum. What do we call that speed? We gave it a specific name. What was that?
Free flow speed.
Free flow speed. Okay, and what about the maximum density? What do we call it? When the speed is 0, you attain maximum density, and we call it what?
Jam density.
Jam density. Okay, very good. So this is just to refresh your minds. So we said m is the slope, which is 65 upon 110 y upon x, and c is the y-intercept, which is 65. So equation of s will become minus 65 upon 110, because the slope is negative, it is going down. Okay, into d plus 65. Okay, and if you simplify it, then s equals 65 will come outside. It will be 1 minus d upon 110, and this one. Okay, I will call it equation 1. I'm calling it equation 1. Okay, can I make it smaller? Yes, I can. Yeah. Sorry, somebody told me that I should use a notebook so that you have the record of the calculations. Okay, I'm trying to use it, so it will take me some time. Okay, bear with me for the time being. Okay, this is the equation between speed and density. It's a linear equation because it's a linear line. It's a straight line. No problem. Okay. Then we have another equation which is v equals to s into d, the basic equation of traffic flow, which I showed you in the previous lecture. Okay, so this equation is also with us. Okay, we also know this relationship. So this is equation 2. Okay, now from equation 2, I can get the value of s in terms of flow and density. From equation 2, I can get the value of s speed in terms of flow and density. So it will be v upon d, right? Okay, then I can put this v upon d into equation 1. So equation 1 will become v upon d equals to, where is it? Just simply take it from here. Okay, and then you can multiply the whole equation with d. So v will be equal to V is the flow, which is equal to, and I'm opening the bracket as well, so it will be 65D minus D square into 65 divided by 110. Okay. And this one is okay. So I will call it equation 3, right? This is the equation, or not yet. You can simplify this ratio. So 65 upon 110 is equal to how much? 65 upon 110. How much?
0.59.
0.59. So the final equation for V will be we'll call it equation 3. Okay, so this is equation 3, which is between flow and density. So now you have the equation between flow and density as well. Going back to equation 2 and equation 1, so I have equation between the speed and density. I have equation between flow and density. So now I need equation between flow and speed. So I will again go back to equation 2, this one, and from this equation I will put D in terms of V and S now. So equation 2 would say that D equals to V upon S. Okay, and then I will put this value in equation 1. Equation 1 says, so I'm talking about this equation, okay? Equation 1 says S equals now this whole thing. Okay. So now I will try to simplify this equation. Okay. So first of all, if I open the bracket, then it will be 65 minus V upon S into 65 divided by 110. Okay, and then I need what on the other side? I need S on one side, everything else on the other side. So I will come here. So it will be V upon S multiplied by 65 divided by 110. And what will be on this side? It will be 65 minus S. Okay, then I will multiply the whole equation with S square, S and 110 upon 65. So this one will be V. This one will be 65S. Sorry, you're multiplying with 110 upon 65, right? So it will be 110. 110S minus, I need S square here, multiply by 110 divided by 65. Okay, give me this ratio, 110 upon 65. How much?
1.69.
1.69. Okay, so I'll just take this equation. Okay, we'll call it equation 4, let's say. Okay, so I have equation 4 equations now. One is between its speed and density, the straight line equation. The other one is the basic traffic flow equation, equation 2. Equation 3 is between flow and density, and equation 4 is between flow and speed. Okay, any questions up till now? Is it clear? Okay, I'll move on. So now I can use these equations to find out the most important parameter, which is the capacity of the road. The capacity of the road. Okay. Now you can see equation 3 and 4 are quadratic equations. They are second degree equations. And remember the curves which I showed you. So you can see flow and density is a curve. Okay, we said speed and density is a straight line. So we had a linear equation. Flow and density is a curve. Flow and speed is also a curve. So both these equations are second degree equations. Okay, so they should be second degree equations because we already said that the relationship between flow and density and flow and speed is followed by a curve. Okay, so curve should have a second degree equation. Now, if I want the capacities, capacity means maximum flow. Capacity means maximum flow. So when I reach maximum flow on any of these curves, what is the slope of the curve? When you reach maximum flow, the maximum point of the curve, what is the slope of the curve at that point? We discussed it in the previous chapter as well, with vertical curves. When you reach the maximum point of the curve, the minimum point of the curve, what is the slope at that point? Yes, go ahead.
0.
Yes, thank you. 0. Okay. So for both these curves, I have the equation. I have the equation 3 between flow and density, and I have equation 4 between flow and speed. What should I do with these equations to get the equation of flow, or to get the equation of slope? So I want the equation for slope of this curve, flow and density curve. What should I do with that equation to get the equation of slope? Going back here. What should I do with equation 3 to get the equation of slope? Go ahead. Yes, anyone?
Take the derivative.
Take derivative. Thank you. So you take the derivative and then put the derivative equal to 0. That will be at the point where the flow is maximum and you have the slope is equal to 0. Okay. So if I take the derivative of equation 3, then equation 3 becomes dv divided by d, and this is equal to derivative will be 65 minus 2 to 1, sorry, not, and this would be equal to 0, right? This would be equal to 0. So from this equation, give me the value of d here. What will be d here?
$55.
55. And the unit of density are, what are the units for density? This is the density, okay? This is density. What is the unit? What are the units of density? Vehicles per what?
Vehicles per hour.
Vehicles per hour density. Think again.
Per mile.
I explained to you, density is like density of a material. Okay, so you measure density as a mass per time or mass per what? Space, right? So it will be vehicles per
Mile.
Yes, vehicles per mile. Okay, so vehicles per mile per lane. Okay. Now, anyone remembers what was the maximum density here, the jam density? In this figure, what was the maximum density, jam density? How much was it?
110.
110. Okay. So if I, and this one, the density, which is where, which is when the flow is maximum. Okay. We called it critical density. Okay. So this is your critical density. This is your critical density. So what is the relationship between critical density and jam density? Can you tell me? Jam equals to what? What is the relationship here? Jam density was 110. Critical density when the flow is maximum is 55.
Times 2.
Times 2, yeah. Okay, so critical density times 2 gives you jam density. Okay, you can mark it as equation 5, right? Okay, now let us find out the critical speed, the speed when the flow is maximum. So again, when the speed when the flow is maximum, then you have to take the slope of this equation and then put it equal to 0. Okay, so you take the derivative. So equation 4 becomes dv ds will be, where is it, 110 minus 2 times 1.69 s, and this is equal to 0. So how much is s here?
$28.06.
28, no.
32.5.
32.5. 32.5 miles per hour. Miles per hour. Okay, and this is the speed when the flow is maximum. So we will call it the critical speed. Okay. And again, going back to this graph, how much was the free flow speed, maximum speed? How much was it?
65.
65. So free flow speed was 65 and critical speed is 32.5. What is the relationship between them? Go ahead.
Again, doctor.
Also times 2.
Also times 2, yeah. So critical speed into 2 will give you free flow speed. Critical density into 2 will give you jam density. Okay. And now, since I have the value of critical, the speed when the flow is maximum and the density when the flow is maximum, I can use them in equation 2. So equation 2 is this one. Is it? Okay, this one. So if you know the value of speed at capacity and the value of density at capacity, you put them into this equation, the flow which you will get will be the capacity. Okay, so when you put the value of critical speed and critical density in this equation, you will get the maximum flow. Okay, the capacity. So give me the capacity. V equals, so I'm using equation 2. It will be 55, 32.5. How much?
1787.5.
17888. Okay, units of flow, meters per what are the units of flow? Meters per meters per mile, meters per hour, meters per what? Meters per road, meters per day. What are the units of flow?
Per mile.
That was density. See here, meters per mile, density. I'm talking about flow now. Meters per meters per what?
Per hour.
Yes. vehicles per hour per lane. Okay, vehicles per hour per lane. So if you want the value of flow rate at some other point of the curve, then you put the speed and density for that point of the curve. Okay, so if I come here, let's say I want the value of flow at point A, then I should take the value of density at point A, and I should take the value of speed at point A to put them in equation 2 to get the value of flow at point A. Okay, so this is how this equation works. Okay, what else? Now, so what I have explained here is how to develop the relationship between the macroscopic parameters, or you can say how to develop your own traffic flow theory models. So you have just developed traffic flow theory models. These set of equations are basically traffic flow theory models. Okay. Now, in some other example, like I will just show you later on, the values can change. For some other highway, you may have a different free flow speed and you may have a different jam density. So you will repeat the same process. The procedure will not change. Okay, the type of equations will not change. Speed and density will be a linear equation. Flow and density and flow and speed will be second degree equations. Okay, but the coefficients, the numbers can change because of the values. Okay, so if you have another highway on which the free flow speed is not 65 but let's say 60, then you repeat the procedure by putting the y-intercept as 60 and the slope will be 60 upon 110 and so on. Okay, so the procedure will not remain will remain the same. Okay, and the linear equation will remain linear, the quadratic equation will remain quadratic, but the coefficients of the equation will change. The coefficient 65, 110, 0.59, these values can change. Okay, but it will still remain a quadratic and linear equation. And this equation 2 is basic equation. You can see here there are no coefficients, so there's nothing to change here. So even if I have another data and data from another highway, this equation 2 doesn't change. It will remain flow equals speed into density because there are no fixed numbers here. Okay, the coefficients of the equation can change. So since there are no coefficients here, so this equation 2 remains the same. Okay, for other equations the coefficients can change. Okay, similarly we have these equations, equation 5 and equation 6, between jam density and critical density and jam free flow speed and critical speed. Again, they will also remain the same because 2 is not a coefficient coming from the graph. 2 is not a coefficient which is coming from the graph. We derived it and we found it to be 2. Okay, so equation 2, flow equals speed into density, doesn't change. Equation 5, jam density is twice of critical density, doesn't change. Equation 6, free flow speed equals critical speed into 2, doesn't change. For other equations, their type will remain the same. Linear will remain linear, second degree will remain second degree, their coefficients will change. The numbers in the equation will change. Okay. And let me go through the terms again. Free flow speed, the speed when density is 0. Jam density, maximum density when speed is 0. Okay. Critical speed, the speed when flow reaches maximum. Critical density, the density when flow reaches maximum. Maximum flow is known as capacity. So this 788 value which we have calculated here, okay, we will call it capacity. Now let us, just to clarify your concepts, I will go through another example. So in this example, they have given me the equation of the straight line between speed and density. Okay, and then there are 3 parts to this question. Find out the free flow speed and jam density. Derive the equations, the other 2 equations, flow and density and speed and flow, and find out the capacity of this site mathematically. Okay, not measuring, we might do it using the equation. Using the equations, find out the capacity of this site. Okay, so 3 parts. Let me copy this equation. Okay, put it over here. Okay, we will start with the first part of the question, which is find out the free flow speed and jam density. Find out the free flow speed and jam density. So free flow speed, how do we define it? This is a speed when what happens?
When density is 0.
When density is 0. So you have the equation between speed and density. Put density equals to 0, it will give you free flow speed. Tell me the value.
$71.2.
71.2. Okay. Then what about jam density? This is the density when what happens? Density at what? Maximum density. When what happens? When do you achieve maximum density? When?
S
Speed equal
equals
to
0.
0.
S equals 0. Very good. If you have the equation, put S equals to 0, you get density. How much?
$122
122, and the units are what?
per mile.
Yeah, good. Okay, first part done. Second part, we need the equations between flow and density and flow and speed. Okay, so equation 1 is given. Okay, and as I said, equation 2 remains the same. So equation 2 was flow equals to speed into density. Okay, so now you drive the equation between flow and density and flow and speed. Give me the equations between flow and density and flow and speed. Use the given equation and this one. The equation is here. Okay, and use this equation like I did. Okay, sorry for this. I didn't know it will all go away. I'm still learning. Okay. Equation between flow. Yeah.
For density, we'll just put the equation instead of this.
Sorry.
For the density, we'll just replace the S with the equation, the 71.2.
No. I don't need the value. I'm talking about the equation. Like we developed the equation 4 and 5 in the previous example. V equals to something into D minus something into D square in this term. So I need equation of V and D, and I need equation of V and S.
Equation between V and D will equal 71.2 D minus D squared
71.2 slowly. Okay, 71.2 D and
minus this, D squared
D square.
multiplied by 0.58.
Okay, good. Then the equation between V and S. Okay, so you do what she must have done is taken the value of s from here, so s equals to v upon d, then you replace s with v upon d in this equation, and then you take v on one side, everything else on the other side, you get the equation between v and d here. Okay.
And the other one will equal 122 multiplied by s minus s squared multiplied by 1.71.
Okay, any questions, any confusion, any problems? We are just following the procedure step by step, which I followed in the previous example. Okay. So from this equation, first of all, take the value of s equals to v upon d, replace it in this equation, okay, and then rearrange it to get the value of v on one side and everything else on the other side. Then from this equation, do d equals to v upon s, then replace d over here with v upon s, and then again take v on one side, everything else on the other side. So you will have the equation between v and s. Okay. Now, so this is the second part of the question. The third part of the question was find out the capacity. For finding out the capacity, we will use this equation, and in this equation I will put critical speed and critical density. In this equation I must put critical speed and critical density. Okay. Now, critical density. For critical density, I will take the derivative of this equation, dv upon dd, and I will put it equal to 0, right? How much is critical density here? Give me critical density. You take the derivative of this equation, put it equal to 0, and then give me the value of density. How much is it?
$61.38.
61.38. per mile per day. And there was another method of finding out critical density, which was what? By using, when I found the critical density here, what did I say then? Critical density and see equation 5?
Times 2. Like critical times 2, yeah.
Yeah, so if I have jam density, which you already calculated, right? You already calculated jam density. So if you can also do jam density divided by 2, it will give you the same answer. Approximately, obviously, approximately. It will approximately give you the same answer, but both approaches are correct. Okay, then to find out critical speed, I will do dv divided by ds. Then I will put it equal to 0. Okay, so how much is critical speed here?
$35.6.
35.6, yeah, miles per hour. Okay, and again we said that critical speed is 2 times free flow speed, and free flow speed is already known. Okay, so instead of doing this, if you have done free flow speed divided by 2, it is also correct. Both approaches will give you the same answer. Okay, so both approaches can be used. Now for finding out capacity will be equal to flow, which is d times s. Okay, so we will use a critical value to find out the flow. Okay, how much is the capacity here?
Two one eight five.
285 vehicles per hour per lane. Okay, so in the previous case we found around 1700 or 1800 capacity. In this case we are finding it around 2185 vehicles per hour per lane. Okay, so it has increased, right? It has increased. Why it has increased? Because it has a better free flow speed. So better free flow speed or higher free flow speed means better design of the road. Whenever free flow speed increases, the capacity will increase because more free flow speed means the road is designed better, less curvature and smooth surfaces and so on. Okay, wider roads and so on. And you can see critical density can also increase the value of capacity. So critical density increase means we have more space available for for the cars. Critical density is vehicles per mile, right? So you have more vehicles, which can come into 1 mile. Okay, so maybe we have more space on the road available on which more vehicles can be accommodated within 1 mile. So this is also increasing the capacity. So if you are using a better design of the road, or the road has more space in terms of width or something, then you will have a higher capacity. Okay, so I'll try to go slowly here, okay, so that you can understand all these terms without any confusion. Okay, so now going for the attendance, and I'm using my phone to take the attendance. I found that their app on the phone is much supportive of the attendance.